Alright, so we'll wrap up the formation of the elements with this video about supernovas. So looking at supernovas is going to explain where the rest of the elements come from, and we'll look at how this happens within the center of a collapsing star. This will help us explain some of the abundance patterns of elements in the universe today. For instance, we'll be able to explain why there's more iron in the universe than there is gold. So in the last video, we were able to explain the formation of elements all the way up to iron 56 based on the processes happening inside the center of large stars during their normal mode of operation. This is sort of part of the life cycle of these giant stars. They start off in these massive nebula, and so they accumulate enough material where they can be 25 times bigger than our sun. Because they're so much bigger, there's a lot more stuff in their center, and then that creates this extended nucleosynthesis that ends up with iron, especially in this red supergiant phase. This then can lead to this catastrophic explosion called a supernova. So we'll look at how that works. So the sort of sequence here for these really giant stars is they live a lot shorter than typical stars like our sun. Our sun has been around for 4 billion years, 5 billion years or so. These really giant stars that produce a lot of these elements, they burn out a lot faster. So they start off burning hydrogen into helium. That's the sort of the main sequence of these giant stars. That only lasts for around 77 million years for a star that's 25 times bigger than our sun. So after they generate all this helium in the core, that helium can start to fuse into carbon. We combine 3 heliums into carbon and then turn that into oxygen. That's going to take 700,000 years to exhaust all the helium that's made, but only 600 years to exhaust all the carbon to turn it into oxygen. So the time scale here is getting a lot shorter. Then we can combine carbon and oxygen in the core, and that can form something like 28 silicon. That process is consumed in 6 months, and then the fusion of 2 silicon 28s to an iron 56, for instance, that's depleted in maybe 5 days. So time is running out for this giant star. And you'll remember here we're in this sort of diminishing returns area where this curve is starting to flatten. There's all this energy released from turning hydrogen into helium-4, and we're able to eke out a bit more energy by turning helium-4 into carbon-12 and oxygen-16, and we reach this peak in iron. So once we reach this peak in iron, any more fusions basically consume energy. So instead of pushing out at the gravity, they're sort of helping gravity collapse the star. And so that's basically what happens here. Once you have an iron core, this force pushing out against gravity goes away. And because gravity is so intense here, these stars are so massive, the star collapses in less than a second. It's around a quarter second for a star to go from something the size of 25 times bigger than our sun to something that's probably smaller than our planet today. This core collapse is really crazy, and it basically forces all the elements in the star to basically occupy exactly the same position, which is a big no-no for physics. And that's going to create conditions where we can start doing this beta positive decay spontaneously. And so that's because the conditions are so intense, the pressures are so high, hydrogen will spontaneously decay into neutrons. So you'll have proton and electron converting into a neutron again. And so you'll have a lot of neutrons in this really tiny space that's on top of this iron core that you already sort of have at the center. So this conversion of hydrogen into neutrons solves part of the problem, right? You have less positive charges repelling each other in a really confined space, but things are collapsing so quickly that that's not the end of the story. Eventually, these neutrons are forced to invade the iron 56 and other atomic nuclei that are in the center of this star. So there's this rapid stage of what's called neutron capture, where these neutrons go into an already existing nucleus, and they create this unstable, very neutron-enriched nucleus. And then what happens is that because these are unstable, some of which are highly unstable, they'll start to decay really quickly. These neutrons will convert back into protons, but instead of being hydrogen out into space, they'll form a new element inside this nucleus. This process releases a ton of energy, and so this rapid collapse is followed by a much bigger explosion out into space that sends material flying across the stars. Just so you understand how this works, so we're going to revisit our chart of the nuclides here. The number of neutrons here is on the x-axis. The number of protons is here on the y-axis. So let's say we're starting with something that something here, like let's call this, this might be iron, it might be something close to it. But then let's say that this is in the center or near the center of a collapsing star. So we're going to bombard it with neutrons here. So it's not going to, the number of protons inside the nucleus isn't going to change, but we're going to add in a whole lot of neutrons. So it's going to come out here. We're so far away from the value of stability right now. Things are going to decay instantaneously in less than a fraction of a nanosecond. We're going to undergo lots of beta minus decay back towards the value of stability. And this, right, beta minus decay is converting neutrons back into protons. And so by losing neutrons, gaining protons, we're sort of moving back towards the stable nuclei that form the heavy elements. And so that process, it can generate cobalt from iron, it can generate nickel from iron, it can generate the rest of the periodic table here in blue through these really chaotic nucleosynthesis reactions that happen in the center of supernovas. But because supernovas are relatively rare, they only happen inside really large stars. These elements that are made in supernovas are much less common than the sort of main group that are formed in large stars. So the Hubble telescope has actually been able to capture supernova events happening in real time. You can see here we're going to start zooming in. This is one static picture, but we're going to turn into a time series pretty quickly. We're zooming on this one galaxy, and you'll start to see the supernova event as it starts to fade away. So this is going to keep going for a few more seconds, and then you'll see a big flash of light. There it is. So that was this explosion following the collapse of a large star. And then what you're seeing here is with that light is all these elements that have been made inside the supernova flying out into space. So anyway, just to wrap up this story, 3 minutes after the Big Bang, our universe was entirely hydrogen and helium, and there was a tiny, tiny, tiny part of the universe that was probably lithium, and that's about it. And after 13.8 years of stellar nucleosynthesis and supernova, here's what we have to show for ourselves. We have hydrogen, we have helium, and then we now have a fair bit of oxygen and carbon. These are the first things that are composed from helium inside stars. And then we have a small amount of things like neon, things like iron, and an even smaller amount of these rare elements that are formed in supernova. So we haven't changed the overall picture here. We've gone down 1% in hydrogen, 1% in helium. But this matters to us because our bodies are made of carbon. Our blood is rich in iron. We breathe oxygen. So it's a good thing that these elements are around. So we can look into the abundance of the elements in more detail by converting to what's called a logarithmic scale. So in a logarithmic scale, basically we're converting powers of 10 here. Each zero is represented by an increased digit here. So if you have a log of 1, that's the same as saying 10. But then if you have a log unit of 2, that's 100 and so on. Conversely, for decimal places, right, if we have 1/10, that's equivalent to -1 log unit. If we have 1/1000th, that's -3. So this is a good way of viewing really large gradients that can't really show up on things like pie charts. So looking here, the scale is logarithmic, and we're covering a pretty big range in abundance here. The most abundant element is hydrogen, then helium, and there's this huge dip for the next three, lithium, beryllium, and boron. These are the elements that are consuming energy if you try to make them from helium. Then we have this increase in carbon and oxygen, but overall, if you compare the abundance of something like helium versus the abundance of something like iron, there's 1,000 times more there's 1,000 times more helium in the world than there is iron. Conversely, if we go over to gold here, which has the atomic symbol Au, this is really rare because this is one of the elements that's made in the universe from just supernova events. And so there's over 10 million times more iron than gold in the universe because iron is made in stars that are functioning normally, and gold is only made in this chaotic way during supernovas. So now we have a sense for where the elements come from, and this is and their abundance patterns in the universe. And this is really key when we're going to start making our solar system in the next video. So just to recap what we did in this video, we found out that the rest of the elements in the periodic table, the heavy elements, come from supernova events. This happened because the conditions are so crazy here. The entire star collapses into a really tiny space, and all of the atoms are forced on top of each other. This encourages hydrogen to turn into neutrons, which invade the nuclei of different elements like iron, and then these decay back to valley of stability to form things like gold. But these events are rare compared to the processes that are occurring every day in stars.